Nous allons donc...
Well, we shall now kick off this panel discussion, which is supposed to last for an hour. We will first have a brief presentation, a couple of slides, just as an introduction to the subject, and then we shall have 4 speakers, the first of which will be speaking remotely. It's in the form of a film, shot by Bertrand Lavédrine, and then we shall have our 3 in-person speakers, and then we shall have a question and answer session with the room, and we shall try, with your assistance, to draw a number of conclusions on the day's topic. So that is how we are going to be organizing things. So, the title of this roundtable, Preserving Cultural Heritage, of course, as part of the broader topic of sustainable heritage management with new technologies and prospects. So we have people in the room who are well versed in these subjects and who are practitioners of these innovations in their own research structure and who are faced with the great difficulties that one may run into, but also the fantastic prospects that exist when one wishes to place research and innovation at the service of the preservation of cultural heritage. Is this working? Yes. The 4 speakers this afternoon, I shall be introducing them when their time comes. I myself am Isabelle Palot-Frossard. Some of you may have seen me this morning, and I'm here as president of the Foundation of Heritage Science. Am I just not? Oh, no. This is working. I'm not going round and round in circles. Not quite yet. So, innovate in order to gain knowledge and preserve in the field of physical heritage. So that requires 4 steps, 4 conditions. The first is that of knowledge. And when I say knowledge, I mean, of course, knowledge of the works, their materials and techniques, knowledge of the alteration, deterioration phenomena, the environment of these works in the broader sense, including buildings, archaeological sites, and so on and so forth. And even more so, more crucially, the issues that professionals themselves face. What are their needs, their expectations from innovation at the service of heritage conservation? And then there's the implementation of these innovations that requires technological monitoring, permanent research on the materials themselves, new materials, of course, older materials, as seen in the first part, but research on new materials and the activation of research of academic and industrial research networks, because innovation, of course, requires a very strong bond with industry. And then, when the innovation comes to fruition and seems to be yielding useful results, it needs to be assessed, it needs to be evaluated in terms of efficiency, durability, and reversibility. Obviously, that's a big problem, as you know, and innocuousness in terms of the preservation of heritage. And then, finally, the results of this process need to be transferred and passed on to the industry and to conservation professionals. So our 4 speakers will each have a specific presentation with specific case studies and results. But if we were to say things in a nutshell, they will be discussing a number of the items I have just listed. So Bertrand Lavédrine, in his presentation, which is a remote filmed presentation, will be giving us a general overview of the issues, and then with Delphine Neff, we shall be discussing the methodology of innovation Ina Reicher will tell us about innovation for better knowledge, development of new tools, of new knowledge tools, and Dominique Martos-Levif, innovation to better conserve and transmit to professionals. And she will more specifically talk about the very tough issue of cleaning heritage, and particularly cleaning paintings. And I have the honor and privilege of moderating this panel discussion. So let us now start with these 4 presentations and keep questions for the end. Of course, the speakers will stay here to answer any questions and listen to your comments. So make a note of what you would like to ask them for later. Bertrand Lavédrine, I think we can now show Bertrand Lavédrine's presentation. Some of you may be familiar with him. He's a professor at the National Museum of Natural History in Paris. And he is a great world-renowned specialist with many publications about the conservation of photographs. Bertrand, for a number of years, was also in charge of the research center on the conservation of collections. And he's going to give us a general introduction, an overview. Thank you, Isabelle. Hello, everyone.
Entre l'Institut des matériaux poreux de Paris et le Centre de recherche sur la conservation au Muséum national d'histoire naturelle. La qualité de l'air est devenue une préoccupation majeure dans nos environnements urbains et une question de santé publique. C'est également un souci ancien pour la conservation des biens culturels. Dès le XIXe siècle, les scientifiques furent appelés au chevet des œuvres qui présentaient des altérations avancées. En 1850, Faraday dénonçait l'empoussièrement excessif des œuvres de la National Gallery de Londres et on notait que des pigments de peinture, jadis stables, n'étaient plus utilisables dans les villes modernes à cause de la pollution. Même les reliures en cuir des livres semblaient affectées. Ce problème ne fit que s'amplifier au XXe siècle. Alors, pour éviter les altérations dues aux polluants urbains et également mettre les œuvres hors de portée du public pour les plus fragiles, on les a protégées par des cadres, des vitrines, des conditionnements adaptés. C'est alors que d'autres problèmes tout aussi inquiétants sont apparus. En effet, les matériaux utilisés pour réaliser ces vitrines, ces armoires, mais également les objets eux-mêmes, libèrent des émanations qui s'accumulent dans un espace clos et peuvent être à l'origine d'altérations. On a constaté des efflorescences à la surface des coquilles, à la surface des perles ou des métaux comme le plomb, le cuivre, l'étain et la ternissure d'objets en argent. Ces altérations, parfois spectaculaires, peuvent être détectées visuellement et leur progression est perceptible à l'œil nu. En revanche, pour d'autres objets, ces altérations ne sont apparentes que lorsqu'il est trop tard pour agir. C'est le cas par exemple pour des polymères naturels comme la cellulose ou des matières plastiques qui s'hydrolysent de façon imperceptible et cette hydrolyse génère à son tour d'autres acides et la dégradation va en s'amplifiant. Les objets produisent des polluants qui contaminent les œuvres aux alentours. Et parmi les cas les plus préoccupants et souvent les plus spectaculaires, les scientifiques de la conservation s'intéressent en particulier à l'acétate de cellulose. L'acétate de cellulose a été largement appliqué à la réalisation d'objets usuels comme les lunettes, des objets décoratifs, des œuvres d'art, mais aussi des films photographiques et cinématographiques. Or, l'acétate de cellulose se décompose après une trentaine d'années. C'est ce que les archives photographiques et cinématographiques ont eu au fait de désigner par le syndrome du vinaigre, en raison de la forte odeur d'acide acétique qui en résulte et qui vous prend dès que l'on ouvre une boîte de film. Mais l'acide acétique n'est pas le seul composé émis. Il y a une multitude d'autres composés organiques volatiles. Et nous avons pu analyser en temps réel les émanations d'une quarantaine de films cinématographiques datant des années 1970 à 1990 et conservés au service des archives du film. La technique utilisée est extrêmement sensible, c'est le PTRMS, et les résultats sont édifiants. On détecte ainsi plus d'une centaine de composés volatiles émis par un film en acétate de cellulose avec un taux d'émission qui peut atteindre quelques grammes par mois, ce qui est considérable. Alors, outre l'acide acétique, on trouve en abondance du butanol, de l'acétone, de l'acétaldéhyde, du méthanol, de l'acide propanoïque, de l'acide formique, etc. Alors, pour éviter une accumulation de ces composés dangereuses, aussi bien pour les œuvres que pour les personnes, il faut purifier l'air. Le purifier soit en ventilant le lieu de stockage avec de l'air frais, soit en piégeant ces composés sur des matériaux poreux. Alors les plus couramment utilisés, ce sont les charbons actifs et les éolites. Alors le charbon actif est peu onéreux, il offre un large spectre de capture. Toutefois, cette capture n'est souvent que temporaire et certains composés adsorbés peuvent être libérés selon les conditions environnementales. Dans les années 1990, les sociétés Kodak et Fuji ont fait la promotion de l'usage des éolites pour la conservation des films cinématographiques en acétate de cellulose. Alors les éolites, ce sont des aluminosilicates d'origine naturelle ou artificielle qui sont poreuses et qui peuvent piéger dans leur pore l'acide acétique. Malheureusement, on a rapidement constaté que ces éolites avaient plus d'affinité pour l'eau que pour l'acide acétique. Et les bienfaits constatés en matière de conservation, car il y avait une amélioration, résultaient surtout d'un abaissement de l'humidité et non du piégeage des acides. Depuis une vingtaine d'années, les scientifiques, et en particulier mon collègue Christian Serre, se sont passionnés pour un nouveau type de composés synthétiques dans lesquels ils placent beaucoup d'espoir, que ce soit pour le traitement de l'air, la séparation des gaz ou pour la biomédecine. Il s'agit des MOF, c'est-à-dire les Metal Organic Frameworks, ce que l'on pourrait traduire par des composés à charpente organométallique. On les produit au laboratoire par assemblage d'une molécule organique et d'un ion métallique, que ce soit du zirconium, de l'aluminium, du fer, du cuivre, du zinc, etc. Alors, cela relève un peu du jeu de construction car on synthétise ainsi des composés cristallisés extrêmement poreux dont on peut décider de la taille des pores et des propriétés en fonction des molécules que l'on souhaite piéger, confiner ou même filtrer. Dans le cadre d'un projet européen intitulé Némosine, différents MOF ont été synthétisés et évalués pour le piégeage de l'acide acétique. Et finalement, le MOF intitulé 1100 a été identifié comme un candidat particulièrement performant. Ce composé, le 1100, présente de nombreux avantages. Il est bon marché, on peut le produire par une synthèse verte à température ambiante. L'acide acétique s'absorbe solidement sur les sites métalliques du MOF et il y a donc peu de risque de relargage. Les tests indiquent que le 1100 est plus performant que les éolites et les charbons actifs. Et non seulement pour l'acide acétique, mais également l'acide formique, l'acide propionique, l'acétaldéhyde, etc. Bref, un grand nombre des composés qui ont été identifiés dans les vitrines de musées, les armoires et les boîtes de films. Les qualités de ce MOF ouvrent d'excellentes perspectives pour la préservation des biens culturels dans les musées, les archives ou les bibliothèques, mais il présente également un intérêt pour la qualité de l'air domestique dans les habitats urbains, que ce soit les appartements, les maisons ou même dans les habitacles de voitures. Il restait cependant un point délicat à résoudre afin de permettre une utilisation aisée. C'est celui de sa mise en forme. En effet, les MOF se présentent après leur synthèse sous forme de poudre et il nous fallait donc les conditionner dans une forme plus aisément manipulable dans les institutions patrimoniales. Nous avons donc proposé au laboratoire une solution alternative plus adaptée qui consiste à incorporer ces MOF dans des feuilles de papier. Les feuilles sont plus faciles à manipuler, à stocker, à adapter à un format de boîte. On peut les découper pour recouvrir une surface d'étagère ou le fond d'une vitrine. Toutefois, introduire une grande quantité de MOF dans une feuille de papier n'est pas une chose aisée, car au-delà d'une certaine quantité, la feuille devient extrêmement fragile et cassante. Nous sommes parvenus à préparer des feuilles contenant 75% de MOF en utilisant de la nanocellulose. La nanocellulose va se disperser entre les particules de MOF et assurer une meilleure cohésion de l'ensemble des constituants de la feuille. Les premières tentatives de fabrication de feuilles A4 ont été réalisées avec le concours des restaurateurs grâce aux équipements des archives nationales à Pierrefitte. Ces feuilles ont été testées avec succès pour leur aptitude à piéger divers polluants. Nous avons également évalué la compatibilité pour le stockage des matériaux photographiques afin de s'assurer qu'il n'y avait aucun risque à long terme. Ces prototypes de feuilles de MOF s'avèrent donc des matériaux innovants à même d'accroître l'espérance de vie des objets sensibles à la qualité de l'air, que ce soit pour un stockage à long terme ou pour des expositions temporaires afin de neutraliser des composés organiques délétères. Pour conclure, je voudrais remercier mes collègues du CRC et de l'IMAP, en particulier les doctorants qui se consacrent à ce sujet, Pierre Tignol et Maria Inès Severino, la Fondation des sciences du patrimoine, la Commission européenne à travers le projet européen Némosine, l'équipe de restaurateurs des archives nationales, les archives françaises du film, l'Institut supérieur technique de l'Université de Lisbonne, en particulier Moïse Pinto et Abir Motar, le ministère de la Culture, le laboratoire des sciences de l'environnement et du climat, l'Institut Lavoisier et la société Weidemann. Je vous remercie de votre attention.
Merci beaucoup.
Thank you very much, Bertrand, for this very broad overview of a very specialized subject. And when we prepared this panel discussion together, you told me how worried you were and thought that it was very generalistic, although you would be facing some great specialists who would probably have some very tricky questions about how MOFs can be used to trap these elements. So, and we both decided that all of these questions were questions that you will have an opportunity to answer when we discuss things with the room. I'm sure that plenty of you have questions. So many thanks for giving us an overview of the multiple partners engaged in an innovation project, academic research with your colleague from the Collège de France, users with the National Archives, the industry who develop the products themselves, and these interfacing laboratories, such as the one which you led, the Centre de Recherche sur la Conservation des Collections, au Centre de Recherche et d'Installation du Musée de France, which very often serve as middlemen, so to speak, in transferring skills and knowledge both ways for these types of projects to work properly. So many thanks, Bertrand. Now let us listen to Delphine Neff. And Delphine Neff, who is, I'm also going to entrust her with this remote control. So Delphine Neff is Research Director of the Alternative Energies and Atomic Energy Commission, the CEA. And she is a renowned specialist in the conservation of metals and their preservation from corrosion. So many thanks for this presentation, which I think will cover the methodologies of innovation. Thank you, Isabel, for your introduction. So this communication was drawn up by a collective of physicochemists working around the issues of the protection of metals. I won't list all of our partners, but you can see that all of the co-authors come from academia and the public sector, except for one who works for a workshop in a restoration company. So, the issue of metals in heritage is, of course, the long term. For those of you who are familiar with corrosion, let me just remind you of the physical-chemical challenges. Of course, we need to work with metals that are materials with specific properties. There are various sizes, various formats. There is ferrous or copper metals, from small objects to large monuments. And corrosion is also something that creates an interaction. There are very different environments. Of course, heritage, there is an atmosphere for the preservation of collections, but they come from diverse environments, some from a marine environment. And when you pull out an object from the sea, it changes the physical chemical conditions, and all of that means that a great number of properties need to be taken into account to develop protection systems to slow down corrosion and make the object more legible. All of this in a context where we are looking for non-toxic treatments, non-toxic for both humans and the environment. So let me go into the finer details of physical chemical aspects. These are objects that we have cut into little bits because we like to go and examine all of the layers. Of course, we do so with permission from the relevant authorities, but to us it's extremely important to obtain more information, because the interest in corrosion and preservation of metals is, of course, to preserve this layer, which very often contains the original surface of the object itself, and therefore we need to preserve the material. Here are a few examples. You have the colonne Vendôme, you have the nails or the crossbars from Amiens Cathedral, heterogeneous materials, complex materials with complex physical chemical features from the scale of the object to the micro or nanometric scale. So it's extremely important to use complementary techniques to understand these materials. So, what does treatment entail? You need to cleanse or create a protective treatment and restore with various procedures, operations, resulting in modifications or evolutions in the physical chemical composition of the corrosion layers. Again, issues of scale are important, micro and nano included. For instance, when you are removing chlorinization from a ferrous metal, that will diffuse a solution within the corrosion layer, and there will be a dissolution or reprecipitation of the mineralogical phase, and you need to understand these processes in order to optimize treatment. So how do we implement restoration processes? In thinking about the issues with colleagues, we have relied on the TRL principle, technology readiness level, developed by NASA in risk management. So we're not as ambitious as NASA, of course, but it's a model that allows us to comprehend how we need to work to transfer technology, and here applied to restoration and conservation when applying a new product or a new protocol. Just very briefly to tell you, the scale breaks down into 9 levels. The first levels are having the idea, a proof of concept, and then level 2 is in the lab. So there, it's more applied, working on a number of samples or samples from historical objects to see if the system works on a more representative scale. Then the final level is, of course, the implementation of the models and on-site treatments in conditions that are directly actionable in order to obtain a proof of efficiency and encourage workshops and people who work in restoration to use them. So these models are well known. You can be trained in these models, but the great difficulty that's been identified is in steps 4 to 7, the so-called Valley of Death, moving from the lab up to the site. And that's where very often public-private partnerships and financial support are required to try to transfer these new developments and make them day-to-day reality. So we have examined a number of our projects, conducted with colleagues in cooperation or each individually or in our own labs, research labs, to show you a few examples and the types of difficulties we may run into. This is a project developed at Nimble-Lapa with a company called Koros about subcritical dechlorration. We moved from prototype all the way to the chamber, restoration chamber in the workshop, and the operational process is now marketed. But of course, the equipment is extremely costly, and not everyone can afford it. So another example, this is an electrolytic brush to cleanse silver tarnish, and there's a prototype here, a design. So we designed the piece of equipment itself, which is sold at cost price by the laboratory, or which can be actually 3D printed in order to obtain it. So that's another development with a self-assembly by the user.
So an example from the Arc-Antique lab with a dechlorration of cannons in situ. So they've implemented an automated device which enables one to look at the dechlorration without having to transport them. So that functions. One of the major issues there is to be able to monitor that at the level of the partner company with regard to maintenance, notably, or more simply an update of Windows, for instance, which may mean that the equipment has difficulties in functioning. Final example with regard to protection of copper alloyed by organic compounds. The first project, it's the implementation of sol gel doped in carboxylate. So there's a proof of concept, a POC, and we need a relay at the level of the conservators to ensure that we can validate that. And a second project is another path of development of LRMH, is to look at the functioning of waxes and varnishes, which are already used, but to restudy them in order to better recommend and put in place reliable guidelines. And then the biopatina plans, which looks at development on-site with a kit which is available, a package which is available, that the research lab provides to the user, to end users. So I will not spend much more time on this, but the idea was to look at how what's important, what's crucial is at this stage of moving from the lab to conservation and restoration. There really needs to be strong levels of coordination of these large consortia, which enables also the possibility of adjusting timeframes, which may be very different between the research world and restoration. And we've also identified a need in training, that is to say, young restorers, to train them to new techniques so that they can be used and implemented. I thank you for your attention. Thank you very much, Delphine, for having presented through these few illustrations, varied illustrations, the process of implementation of research and innovation in order to really bring to the fore the issues, difficulties which exist at the Death Valley stage, which is often difficult to go through. Thank you for this presentation. Because time is of the essence here, we'll move directly to the presentation of Ina Reich, who's research director in the chemistry of ancient materials, and who's also the director of the new AGLE, accelerator of particulates of the CNRS. And there are several bows to her arc, we can put it like that. Several it's development of new tools of analysis. So it's for you. Hello, everyone. Hello, everyone. And thank you very much, Isabel, for this presentation, this introduction. I'm delighted to be here with you today, to having been invited for this to talk about this research project, one of our research projects. Which is to do with the conservation, restoration, and preventative conservation of works of art, the original appearance and beauty of ancient paintings virtually reconstructed. So there's a whole team, of course, from different colleagues, old restorers, physicals, specialists, chemicals, PhD students, academics in France and Germany who have contributed to this project that I'm presenting here today. So generally, when you talk about new technologies for heritage, it's in an interdisciplinary context. We go from knowledge which has been built up over many years, which have enabled us to carry out different technological developments. I'll be presenting some today in the context of this, the case studies, most recent technologies that we use, and I'll illustrate that with a painting which is currently being restored. To illustrate the different possibilities that exist today to contribute to preserving cultural heritage. So the general idea, we've mentioned this already this morning, we've touched upon it. We are trying to contribute, we're looking to contribute through our physical and chemical markers looking to contribute to the heritage sciences by creating new criteria which might not be visible to the naked eye, but which are based on the structure of the objects, their chemical structures, and we create a new knowledge around the works of art, which then enables us, in collaboration with the other colleagues, to respond to different issues, questions around heritage. It might be a better knowledge of the work through the identification of the materials used, maybe also help to establish mechanisms of alteration, which may be occurring. We try and do that in the less invasive way possible. We're trying to establish those approaches. We also look at trying to understand what makes a material change over time. And like that, we have criteria which enable us to say, this is what we need to work on, to be on top of, to control, to avoid alteration over time, and what materials also can be used for preventative purposes, and many tools that we have at our disposal. That's also been illustrated this morning very well in the plenary session. It enables us to establish references which are also worked on over time. That is to say, we create digital databases, which enables us to have the different stages of conservation of the works of art, and so we can have a better assessment of how they're going to evolve over time and if they're going to evolve over time. So I'll show you this in this introduction that is absolutely in that approach, an integrated interdisciplinary approach. So of course we don't apply new technologies just for the sake of it. We're doing it because we want to respond to answer several questions, a number of issues that are looked at to improve knowledge, and the analytical approach that we use depends, of course, on the context, the type of artifact, where the artifact is. Do in situ analysis need to be done? Does it need to be transported elsewhere to a lab? Do we need to carry out analysis with instruments like a synchrotron or a particulate vacuum? All that needs to be taken into account account to establish the strategy best adapted to really enable us to answer the question posed. We don't need to do things when things can be seen with the naked eye. We need to ask ourselves the right question to develop the right strategy and the most adapted strategy. For that, for many years, at least since the 1970s, technological developments have occurred to improve the analysis of works of art. Some may have been forgotten already, but for instance, the first imaging of works of art was done with the neutrons. So, for instance, there's the neutronic activation, which has enabled us already to look more closely and in detail at paintings, and that has been developed by a number of with the particulate accelerator. And another huge development was the use of X-ray devices with synchrotron sources, but also lab sources and devices, which today mobile. I believe that everybody has heard the talk of the development of the methods of MA XRF and bifocal micro XRF, for instance, when we want to look at the paintings in detail, in 3D detail. There's also another way, bifocal mode, which has been developed by our teams to confocal micro XRF to be able to analyze the works of art in 2 and 3D in a completely non-invasive way. And so today we go even further with the same device. We can combine the different types of analysis. For instance, the MA XRF, big spectral, with the creation of big spectral data sets. Spectroscopy X, for instance, and also fluorescence X in 2D and in confocal mode. So we really have tools which are highly performing at our disposal in order to be able to study in a non-invasive way artifacts. But the difficulty that can occur and that we find ourselves confronted with, it's not the analysis itself. Often, sometimes it's time-consuming, but that is something which we can take on board. But it's the storage of data. There's a creation of a huge spectral data sets, and they can that can be the difficulty today. And the projects that I'm going to be showing today, it's an example which shows where these techniques can come together, and also shows the development of the different ways of assessment which are necessary to really understand the objects in their context and be able to answer the questions that are put to us. So the example that we're going to this is a project we're working on. And I'm working on this project currently, and in the context of this project, we're looking at this painting, which is in a state of painting. Which it's from the school of Fontainebleau, which dates back to 1570, an anonymous painter. But it has a smelt in it, and it's a blue pigment. In effect, it's on cobalt-based, and that we know that it alters over time and changes color. So it's difficult to recognize it on the artifacts and the paintings, and it really changes the perception that you can have of the different paintings. So first we applied the fluorescence X as an imaging mode, so to map the different chemical elements present, so to see where this smelt pigment is on the painting. So different processing of data to identify the different components present, and then we look at the different characteristics of the elements which exist. We can calculate the spread out of the different elements on the painting itself, and then we can compare that chemical breakdown with the painting, with the photo of the painting, and the smelt can be recognized generally, can be identified by these four elements there, cobalt and potassium, also nickel and arsenic. and even if the smelt is altered by these chemical mapping, we can recognize and reconstitute a chemical composition which we can deduct because of the different pigments which exist in the smelt and also the pigments present on the painting. So here we have deducted that there was a smelt to these areas in the painting, and then as we're focusing on the original appearance and beauty of ancient paintings, which we want to reconstruct virtually, we need to look at the coloring, the chemical elements. That doesn't give us that information, so we combine that information with a spectroscopy of imaging. With reflectance imaging spectroscopy, I can't go into detail here, but there's also a digital processing of the different specters, which enable us to calculate the presence of the different pigments present, to confirm also the presence of smelt. We suspected there are two types of smelt in this painting, and in effect, with the hyperspectral analysis, we can confirm the presence of smelt in these areas, but it's not exactly two types of different smelt, but in effect the smelt was used in two different manners for the painting, and that all of this knowledge has helped the restorers to restore it, to restore the painting, and to know exactly they've removed the varnish, and that helped them to really decide what needs to be touched upon and redone. And I find the result quite spectacular, personally. And this was a fantastic collaboration to contribute directly to the conservation and restoration of this painting. So this is ongoing work. It's an example. We're still working on it. We're really looking at working very closely with the colleagues and the conservators and the restorers to really provide all the tools that we have to hand and to know better the paintings and really conserve them in the best possible way. And we're really focusing on the digital processing of data and the data fusion. And I believe that it's something which is extremely promising because it enables us to really reconstruct virtually the artifacts and to propose different states and different manners in which we can conserve them. And then the restorers can really decide concretely how they're going to restore the artifacts and works of art. I thank you for your attention. Thank you very much for this presentation. Ina, you showed us that what we consider like technological tools that we implement in labs are here to better know the works of art, but you don't always see the exact different link with the restoration. So thank you for illustrating that the work you do in collaboration will enable us, maybe once the work is really completely ready to really work even better on the cleaning and the restoration of some paintings. So we will now greet Dominique Martos-Levif, who's a research engineer and head of the painting restoration workshops at the Center for Research and Restoration Museums of France, and also works as a restorer of paintings. That's how we first met originally. So, Dominique, you're going to be talking about cleaning. Hello. Thank you, Isabelle, for your introduction. So the cleaning of paintings is an irreversible action which is looking to reestablish the visibility and the state of presentation of the works of art. In France, we use essentially methods, chemical and mechanical methods of cleaning, and it's sculptures and architecture is more done with laser. So now we're going to be talking about the cleaning, the laser cleaning, with the example of the frames of the Retable of Isenheim. The Retable d'Isenheim is done probably between 1512 and 1516 by the painter Matthias Grudewald and the sculptor Nicolas de Haguenau. It was transported to Colmar in 1793. Today it is at the Interlinden Museum of Colmar. So the work is made up of 11 panels of wood, which are painted with mixed techniques, with structure which is multicolored. It has been restored several times, the Retable. It has been studied notably by the scientists of the DRAC since 2019. There are 21 restorers, and it's Anthony Pondabry and Juliette Lévy for the sculpture who are working on this. The interventions of conservation, of restoration. We're looking to improve the structural state of the work and its visual aspect and aesthetic, cosmetic aspect. This campaign, there's a scientific committee and a steering committee made up of the specialists of the history of art, sciences and materials and techniques in the restoration. I would like to seize this opportunity to thank the director of the Interlinden Museum and the team of restorers who've helped us throughout the course of the campaign of laser tests. We will be looking here just at the issue of the elimination of the overpaints which were over the crucifixion of Saint Antoine and Saint Sebastian, which are the panels you see here on the screen, because the cleaning of the painted frames and the other elements was done chemically, but there was no big issue. So we're looking at the repaints, the tests of cleaning carried out by the restorers with chemical methods or mechanical methods on the frames which present fake marble decor. They gave bad results. The outcome was not good. That is to say, with regard to the fact of harmlessness and the visual aspect, it wasn't entirely satisfying. So in 2019, the CNRS was asked to see if they could do work on with the laser on the repaints. Those were done by an Italian specialist, a specialist in laser. Laser removal in painting, with, of course, in collaboration with the team of restorers. The CNRS was there to steer the tests, to give a framework, and give a scientific assistance in order to assess the protocol of treatment. So when you carry out cleaning, when we're looking to get out to look at the repaints, you have to look at the different layers and eliminate the ones that need to be eliminated, the ones that need to be retained, and see how sensitive they are. In the context of the campaign of laser cleaning, sampling was taken. They observed in binocular magnifier. And you can see here the stratigraphy of the lateral panels, and so that the different layers are made up of several layers. You have preparation layers with the original false fake marble, which was done à tempéra, and then there's a second state which corresponds to the repaint, which was done later on with oil, and everything has over it another layer. You can see at the top the two horizontal, the two crossbars of the predella, which come later on, and those they were replaced. We don't have a date when the replacement occurred, but on those two, we can just see one state of false marble and two layers, two monochrome layers, single color layers. The objective was to bring to the fore the original paints, and for the predella at the level of the crossbars to have the later false marble, fake marble come to the fore. So two types of lasers were tested. one at 1064 nanometers that was used in SFR mode, short free running, and also in long Q switch to have an action which is either more or less photothermic. And then there's also light brush 2 at 2940 nanometers with impulse, which was short or very short, which can be chemically destructuring. The control of the cleaning was ensured by tomography in optical coherence, so there's no contact there. It's non-invasive, based on the interference of light with the matter. So that enabled us to see what the level of cleaning was from a stratigraphic level. The visual information and photos which were looked at under Dinolight in order to assess the efficiency and also the harmlessness levels of the cleaning. So from a methodological point of view, the laser cleaning is done in the same way, it's approached in the same way as the chemical one. So the restorers intervene always in a progressive manner when we're talking about chemical restoration, to ensure they don't alter the original painting. The objective is to provoke the dissolution of the materials that they're looking to eliminate by playing on the different parameters, such as polarity or the pH dissolving of the different emulsifiers or gels they may be using. Like in classical approaches, it is possible by looking at and varying the parameters of the laser, the level of efficiency of to modify the mechanism of efficiency. Laser materials, you can obtain levels which are either more or less thermic, mechanic, or photochemical, and you can then you can isolate some materials and eliminate them while preserving the original painting. I've chosen to present just two cleaning tests. The first one, which you see on screen, was carried out with a laser ND YAG. YAG, sorry, which is at 2,940 nanometers, so that destructurize progressively the matter. Its use upstream from the chemical cleaning enables one to limit the use of solvents to avoid the material residues. You can see an OCT picture underneath, which gives an image of the painting, and you can see the area which is non-cleaned. You can see at the top a very white surface. That's the interface between the material and the air, which is due to a change of the optical index between the different environments. Underneath, you can see a light which is not as saturated, which is the interface between the different structures in what is cleaned with the YAG. You can see on the right, you can see that the surface is irregular, and you can see that the light is being diffused. And you can see that the images under Linolight, which are presented at the top, shows that the cleaning remains incomplete. The area which is cleaned with the ND YAG on the left has a totally different aspect. The interface air matter is, you can see that the light is being less refracted. And here I'm presenting a detail with there's cleaning with the ND YAG here, 1064 nanometers. You can see the different layers there between the repaint and the original layer. It appears it appears clearer here than on the preceding one, because the mechanical action of the laser brought about a level of cleavage between the layers. So the photos taken under Linolight show that the original polychromy is in a satisfactory level of conservation. So it was decided to use this laser to really clean up all the frames that were looking to be cleaned. So this study shows that the laser can be considered as an additional tool for the restorers of paintings. So it can solve several issues of cleaning, and like water products, water-based products, it's more harmless. And as we've also understood better the mechanisms of interaction, laser light, and we can then assess the cleaning of the paintings. So it appears, the laser appears to be a tool which is totally adapted for the control of cleaning, and you can assess it from a layer-based level in the context both of laser cleaning and chemical cleaning. So the work needs to be carried on with this to better understand the phenomena of destructuration of matter and compare them with the mechanisms of dissolution which are brought about by solvents. It is also necessary to establish a database on the optimal parameters of using of the laser with regard to the different materials in the paintings and artifacts, and to pass on the knowledge and to train restorers so that they can really take this on board, this new tool. I thank you.
Thank you, Dominique, for showing that advances over the past decades in laser technology have added this as part of the restoration toolbox, not just for stonework and sculpture. So let's now move on to the conversation with the room. Could we reconnect with Bertrand Lavergne? Okay, Bertrand is with us. So perhaps we could do this for each of the presentations. Are there questions for Bertrand? If you could please introduce yourself for the other ones. Hello. I'm from the Restoration Department of CDMF. I have a question from a non-scientific point of view. Did you hear me, Bertrand? I think it would be better if you started over. Yes, I can hear better now. So, Mireille Klein, C2 RMF. I have a question for you, a pretty basic question about MOFs. Are you quite sure that there is no option, that there's no possibility of a re-release of volatile organic components, as was the case for charcoal or zeolites? You said that was problematic, but for MOFs, are you positive that there can be no re-release? Let me just specify, I don't know if you have this on screen, but we have a great specialist of MOFs here, but our investigation of this particular type shows that acetic acid is really retained. It may not be the case for all volatile organic components, but it's definitely the case here. Christian, would you like to add something? Well, of course, there's the absorption of chemicals, which can be absorbed at relatively high temperatures, but in an ambient temperature, no, there's no release. So we need to wait for industrial production so that we can test it in our storage. Yes, well, that's exactly what Delphine was saying. We are in the Valley of Death, the so-called Valley of Death at the moment. There are multiple types of innovation presented today. Some are closely related. You can take something that's off the shelf and use it in the field of heritage conservation. And then there are incremental innovations where you can use technologies already available in the labs. And then there are radical innovations which start from stage one, and we're trying to bring it all the way. And that is pretty much what we did with Christian. It was a great experience in MOFs. And then, of course, this needs to reach a certain level of maturity. in order to pass over to the industrial level. And we had this experience with Christian. We're told, oh, yes, but these are niche markets. We're not going to be making a profit out of this. And the only support we're getting was not from the industry, but from foundations who were probably doing it for their own image. But that is the only way for us to try to develop radical innovations. Let me just pick up on that. Some of these materials are currently under consideration by startups and so on to be produced, say, a couple of 100 kilos, but for more conventional uses such as heat pumps or catalysts. But that can only be beneficial if we want to use these materials cheaply in conservation. Yes, of course, niche market. Of course, the preservation of heritage is not a particularly buoyant market from an economic point of view. So we only have 7-8 minutes left, because then the participants need to perhaps move from here all the way to the Louvre for the following session. So a tight schedule. Another question. Do you have your microphone, Marie-Noël? Hello, Bertrand. Marie-Noël Laurent. I'm a painting restoration. There's ongoing research in that field, and we're running into very big problems in the paint on canvas becoming very brittle with acidification. So very, very fragile, brittle. So what can we do in terms of preventive conservation? Some tests on the deacidification of these canvases were conducted before they were entirely lost. Do you think it would be possible to place perhaps moth-impregnated sheets on the back of these canvases to deacidify them, to stabilize them? Thanks for your question. Very briefly, I don't think it could do any harm if it absorbs the acid volatile components, but moths are essentially made for confined environments, closed environments. So, of course, if the painting itself is, if there's a protective backing, for instance, yes, for instance, if there's a protective backing, it might make sense. Otherwise, not so sure. I think testing would probably be the best thing to do. A new research subject, or adding some sort of membrane on the back. It could probably do that and slow down the deterioration, but I wouldn't want to commit to anything because we have absolutely not tested that. An interesting research prospect for years to come. So we are eager for a proposal for a grant from the Fondation de la Science du Patrimoine. So I need to be a very strict timekeeper here. Do we have questions for Delphine Neff about the methodology of innovation, corrosion, protection of metals? No questions? No questions in the chat feature? Perhaps allow me a comment about the previous presentations. I think your question to Bertrand Lavedrine is very interesting because I face that type of problem on a regular basis. We have these restoration professionals, they come along and they have a little question about what can we do, this or that. And it's true that it would be a research project in its own right. You have a problem, a very complex issue, and that requires a conversation, a dialogue, to try and identify things that make sense for the greater number. We can't look into every tiny little specific detail, and sometimes restoration professionals are disappointed, or sometimes disappointed with the responses given by chemists. And I think we really need to discuss the issues more broadly, to not necessarily with a view to make something fully leverageable by restoration professionals. But I did have a question about the infamous Valley of Death. How do you think you can unlock the road to marketing these solutions or products? How do you think this little lock can be overcome? Years after I started wondering, I still have not unlocked or found the key to unlock this solution. Of course, I try to involve restoration professionals as much as possible in the development, allow them to follow or stay informed of the research process. And then when I do end up with a product that seems to work, is people say, yes, well, where can I buy it? Because very quickly they have a construction site, a restoration site, and they want to be able to use it. And I think that probably experience-based restoration might also be a good way to involve restoration professionals in the process in the long term, in order to, and I also need feedback from restoration professionals. I can develop lots of products, as many products as you like, but are they useful to them? If I don't have a professional who says, it's a good product, but it's too difficult to use, it needs to be, all the various components need to be mixed, and that's impractical on our restoration site. I need that sort of feedback to know whether solutions proposed are or not practical, or in terms of their feasibility. And that takes time, of course. Yes, you also have a comment, Dominique. Yes, I just wanted to add that I think the crucial question here is funding research in restoration, because restoration professionals are interested. Yes, I think that would be a good subject for another roundtable. But yes, I suppose we could do something about the transfer, not necessarily just the innovation itself, but also transferring innovation towards the end user and industry. Of course, restoration professionals, restorers can be involved in the process, but in the industry usually turns up at the end of the chain, and it's very hard to follow through all the way to industrial production. And that's probably the most difficult bit. So I think we could probably take one or two more questions, and then we'll need to stop and move on to the next round table. So, Marta Castillero.
I have a question for Dominique. You are removing the overpaint over the real paint layer that you want to preserve.
Yes, we preserve the real painting.
Yes. Aren't you? Est-ce que vous êtes concerné par le
Are you concerned by the transmission of infrared laser to some layers? Because infrared laser may cause damage.
Oui, nous avons fait des tests et...
Yes, indeed, we have tested that, and we have not run into any issues with the infrared laser. There really is there's a mechanical cleaving, and it actually comes detached. It's very low energy. Okay, I'm terribly sorry to have to interrupt this exciting debate, but unfortunately we'll need to leave it here. Because all of the other roundtables have ended already. Sorry, I've been a very poor timekeeper. Many thanks to all of you.
Merci à tous.